Welcome to Calculations module, Ventilator Variables. In this module, we're going to cover compliance, both dynamic and static compliance, airway resistance, inspiratory time, peak flow rate, and calculation of IE ratios. Okay, then let's look at dynamic compliance. And again, you can see that in this example, it's the tidal volume divided by your peak pressure minus any PEEP. And the dynamic compliance measures the elasticity of the lung during air movement. It's actually a less reliable indicator of lung elasticity compared to static compliance. So we're going to use the peak pressure when we calculate dynamic compliance. Static compliance, on the other hand, is your tidal volume divided by your plateau pressure minus any PEEP. And your plateau pressure is that pressure that we looked at on the graph earlier that represents a state of no flow. Static compliance measures the elasticity of the lung when there is no air movement. It is the best indicator of the ability of the lungs to ventilate. And the normal static compliance is around 60 to 70 milliliters per centimeter of water pressure. So the plateau pressure is also referred to as the static pressure. So what exactly does compliance tell us? Well, again, change in volume, that's in milliliters, over the change of pressure, which is in centimeters of water pressure. And compliance tells us that for every 1 centimeter of pressure, the lungs can hold X amount of air. So the more milliliters of air that the lung can hold at a given centimeter of water pressure, the more compliant the lung is. Let's look at examples here. Patient A has 30 milliliters per centimeter of water pressure, and patient B has 60 milliliters per centimeter of water pressure. Patient B has more compliant lungs. Patient A lungs can only hold 30 milliliters of air for every centimeter of water pressure, whereas patient B lungs can hold 60 milliliters of air for every centimeter of water pressure. So let's attempt to do a compliance calculation, and in this example let's calculate your static compliance given the following variables. In this example you have a number of variables: FiO2 60, peak pressure 38, tidal volume 600, rate of 12, plateau pressure 29, and PEEP of 5 centimeters. Since we're doing the static compliance, remember we're going to use the plateau pressure, and in this case we're also going to utilize the PEEP because we have to subtract it from the bottom. So then we would take the 600 divided by your plateau pressure, which is 29, minus any PEEP. And if you calculate that out, your static compliance for this example is 25 milliliters per centimeter of water pressure. Well, in example number 2, we're going to calculate the dynamic compliance, and the only difference here between the static compliance formula and the dynamic compliance formula is that we are going to utilize the peak pressure of 38 rather than the plateau pressure. So we incorporate the same formula, and we take the tidal volume and divide it by the peak pressure divided by any PEEP. In that case, it's 600 divided by 38 minus 5. So in this example, the dynamic compliance is 18.18 milliliters per centimeter of water pressure. In this next slide, we have a little bit of a scenario, and it involves Mr. J, who arrives in the emergency room in acute respiratory distress. He was subsequently intubated and placed on a mechanical ventilator. And in reviewing Mr. J's ventilator sheet, we see the following information, which is his plateau pressure at 8 a.m. is 22. And you'll see right off the bat that as time goes by, his plateau pressure rises from 22 to 27 to 31. The other variables, being PEEP and tidal volume, remain the same. So the question is, if we have the rising plateau pressure and our other variables are remaining the same, what does this information reveal about the compliance of Mr. J's lungs? Well, the answer is right here. If you plug the numbers in to the static compliance formula that we covered, you will see that as his plateau pressures rise, his compliance falls. A decrease in compliance is consistent with increasing chest wall resistance. When you think of compliance, you should think more closely related to peripheral chest wall as compared to the next slide, which we're going to look at, and that is airway resistance. Airway resistance is within the lumen of the airway, and you can see that in this diagram, the normal airflow, there is no obstruction. But in this diagram, there is actual obstruction to airflow, and the air has to go through the airway in a narrowed opening. Therefore, the gas that opposes it is resistance, and you get an increase in resistance, or excuse me, the force that opposes the gas flow basically equals airway resistance. Now, the normal airway resistance is 0.6 to 2.4 centimeters of water pressure per liter per second on a non-intubated patient. And on an intubated patient, it's closer to about 5 centimeters of water pressure per liter per second. Okay, so let's look at the formula for airway resistance. It's a fairly simple formula, and that is you take your peak pressure minus your plateau pressure and divide that by your flow rate. Now, before you can do that, though, you must first be sure that the flow is in liters per second. If the flow is given in liters per minute, which is how most of your ventilators are set in liters per minute, then you need to divide the flow rate by 60 before you place it in this equation. So in this example, if the person was on 60 liters per minute, in order to calculate air resistance, you would then divide that by 60, which would be 1 liter per second. And therefore, you could put that flow rate into your equation, your peak pressure minus your plateau pressure divided by your flow rate. So let's try it in an equation. Calculate the air resistance given the following parameters. And you can see we have a variety of parameters, but remember, there's only certain parameters that we need to utilize. In this case, we need the peak pressure, the plateau pressure, and the flow rate converted. So the first step really is to convert your flow. You can see that the flow is given in 40 liters per minute. So in this case, we need to convert it to liters per second. So we take 40 divided by 60, and now we have our flow rate in liters per second. So in this example, we have 0.67 liters per second. Now it makes the equation very simple. We just take our peak inspiratory pressure, which is 38, minus our plateau pressure, which is 29, and divide that by the 0.67, which we get an answer of 13.43 centimeters of water pressure per liter per second. We said the normal resistance was around 5, so this is obviously a little bit high. The number is 13 in this case. There are a number of factors that could cause your air resistance to rise. Obviously, any obstruction of flow, and when you have a person on a ventilator, there are a variety of things that can do that. Bronchospasm being one, retained secretions, biting the endotracheal tube, too small of an endotracheal tube. These are just a few of the examples that could result in increased airway resistance. Well, this next equation is a multi-function equation, as I refer to it, because it'll allow you to calculate either the I time, the peak flow, or the tidal volume. And you can see that we have it set up where the tidal volume in liters divided by your I time is equal to your peak flow divided by 60. So depending on which variable that you need to solve for, you would set it up in a basic algebraic expression and solve for x. In the next example, let's take a look at how we would find our inspiratory time if we had the other three variables. Okay, so let's try to let's try to calculate our inspiratory time. And you would know that the inspiratory time is the inspiratory portion of the breath. In other words, it's the amount of time spent in inspiration. So to find your I time, you first determine the length of a single breath, and then you use the I ratio to determine the length of the inspiratory time. So let's use this example to calculate our I time. Let's look at the parameters that we have, remembering the equation as well. But we have a tidal volume of 600, peak flow is 60, FiO2 is 60%, which we don't really need, rate of 12, which we do need to get our total time, and an IA ratio of 1 to 2. So the first thing we need to do is determine our total time, basically. That's fairly simple. If the person is on a rate of 12, well, you divide 12 into 60, and you get 1 breath every 5 seconds. So that should make sense to you. Your total time is taking your rate and dividing it into 60. So the total time for each breath cycle, inspiration and expiration, is 5 seconds. Now that you know that you have a 5 seconds total time, you can then use the next part of the equation, or the next setup here, is to determine the inspiratory time. Well, in order to do that, you set up a basic algebraic expression, and you will see that 1x plus 2x equals 5. Now the question you might be asking yourself is, how did you get 1x plus 2x? Well, let's go back to the I ratio. We said we have a 1 to 2 I ratio. That if that was different, if it was 1 to 3, it would be 1x plus 3x. So since they're saying one part is inspiration and 2 parts is expiration, we set it up by going 1x plus 2x equals 5. That's the 5 seconds. Then we have 3x equals 5. And then we divide by 3, and we get x is equal to 5/3, or 1.67. So our inspiratory time is 1.67. So then it's obviously very easy to get our expiratory time, because we know that the total cycle is 5 seconds, and we would subtract 5 seconds minus 1.67 seconds to get our expiratory time. But in this example, we solved for inspiratory time. Again, just to review, why did we have 1x plus 2x equals 5? Well, that's our I ratio was 1 to 2. So we put those two down. We have 3x, x equals 5/3, or 1.67. That's how you calculate your inspiratory time. Well, what if we had to calculate the peak flow using the same formula? Well, the first step is to calculate your I time, and we did that in the previous slide. But for this slide, we'll say that the I time was calculated to be 1.14 seconds. We have the parameters, tidal volume 750, respiratory rate 15, I ratio 1 to 2.5. What we really needed was the I time, and once we have that I time, from utilizing our equation to calculate our I ratio, we would then plug our I time into this equation. So we have our tidal volume, which needs to be in liters. In other words, if the tidal volume is 750, make sure that you put 0.750. That's an important part of this. If you don't put it in liters, it will result in an erroneous answer. So tidal volume in liters, 0.750, divided by our I time, which we calculated from our previous equation. And we plug this in, and we have 0.750 divided by 1.14 equals x, because we're trying to find peak flow. That becomes our x over 60. Well, then we do a simple cross multiplication, algebraic expression, and we take the 0.750 and multiply it by 60, which then would give us 1.14 times x, and what we end up with is 45 divided by 1.14, which gives us a peak flow of 39.47. Let's go through that one more time. Remember, we take the 0.750 and multiply it by 60. And when we do that, we get 45. That's where the 45 came from. And we take the 1.14 and multiply it by x. Then we divide. Okay, we have the 45 divided by the 1.14, which gives us a peak flow of roughly almost 40 liters per minute. Well, this is using the same equation again, but we're finding a different variable. In this example, we're going to find the tidal volume. given the peak flow, respiratory rate, I ratio, and most importantly we needed to calculate that I time because it's the I time that we need in the formula. So here obviously if we're looking for tidal volume becomes the X, and now again we do the simple cross multiplication and we have the tidal volume times the 60, so we have 60x, and we have the peak flow times the inspiratory time, so we have 50 times 1.43, which comes out to about 71.5. So then we divide 60x over 71.5, and we get x is equal to about 1.1917, or in other words, it's a rather large tidal volume, almost 1200 milliliter tidal volume. So again, you can solve for any one of these variables by simply setting it up in the equation if you have the other two variables. Okay, let's do the last example, and that is to determine the I ratio for a patient on a ventilator, breathing 20 breaths per minute, tidal volume 600, peak flow of 50. Well, in this example, we have the peak flow, which is 50. And we also have the tidal volume, which is 600. So we need to calculate your I time first in order to be able to calculate your I ratio. So again, we plug our numbers in, and we have the tidal volume of 600, and we would convert that to liters, remember, so that's 0.6 right here. And we would be multiplying that by the 60, and then we would take our peak flow, which in this case is 50, and we're going to multiply it by X. And by doing that, you should know now that if we calculate that out, 50x times the 0.6 times 60 will come out to 0.72 seconds. Well, since we have an I time of 0.72 seconds, we need to calculate the total breath time, which is very easy. Remember, the total breath time is taking your set rate and dividing it into 60. So in this case, we have a total breath time of 3 seconds. Well, now that we have the total breath time, it's easy for us to get the expiratory time because we're going to take the 3 seconds and subtract 0.72 seconds, which is the inspiratory time, which will give us our expiratory time. You'll see that's what we just did. We have the I time of 0.27 seconds. We have a total breath time of 3 seconds. So we need to remember that our total breath time is composed of both inspiratory and expiratory time. Therefore, our total time minus the I time is equal to the expiratory time. So we simply take 3 minus 0.72, which is equal to 2.28. So we have an inspiratory time of 0.72, and we have an expiratory time of 2.28. So we need to convert this to a 1 to X ratio. And again, we just take the 0.72 to the 2.28, and we divide it by 0.72. And when we do that, obviously, the 0.72 equals the 1, and we got 0.72 into 2.28, which would give you 3.2. So it's a 1 to 3.2 ratio. Okay, that's the end of this module on ventilator calculations. I hope you found it very useful. And if you review it a number of times and practice it, I think you'll become very efficient at calculating not only I ratios, but determining your flow rate, your I time, and your compliance.